Seeing photons in color. Before we get into the paper, we first need to know what a SPAD is. Single photon avalanche diodes are a type of image sensor that can record individual photons with very precise timings. These have been applied in many fields like LiDAR and medical imaging. So currently other researchers have been able to put SPADs together in an array to record up to 3.2 megapixel images up to 100,000 frames per second. These arrays capture monochrome binary frames that are very mosaicked. To get colored frames, we can use an RGBW color filter array to activate the diodes on specific colors. But because each frame is in binary and very mosaicked, we need to combine these frames together to get a full image. However, traditional burst photography algorithms don't work because parts of the image can move between different colored diodes. This paper proposes a solution for combining these frames and finding the best color filter arrays. The naive approach of taking the average over every image doesn't account for the motion and results in very blurry images. Therefore, we must demosaic, find the motion between the frames, and then finally merge them to get a usable image. However, doing these steps sequentially in either order results in a poor quality image. Therefore, the researchers propose a joint merging and demosaicing algorithm. They first use an estimated blockwise motion to warp a grayscale block sum image to create a reference image. Then, this reference image is used to guide the merging and demosaicing of the initial images into separate RGBW images. These are then combined into a full RGB image using W as the luminance. Another issue when using SPAD arrays to capture images is hot pixels. These are specific diodes with an increased dark count rate, or more simply, they activate without detecting photons more than the diodes around them. These hot pixels cause errors in the motion estimation and lead to streaks in the final image. The authors propose a chrominance-focused denoising method that uses the W channel along with a calibrated hot pixel map to do the denoising. The researchers also sought to find the best color filter arrays to use. Here we can see a comparison between a regular filter, a random filter, and a pseudo-random blue noise filter that the paper proposes. We can see that the regular filter produces more color artifacts in the static image, while the proposed filter produces less, even in the higher frequency components. Overall, the proposed filter works best over all the motion conditions. They also found that the minimum amount of motion required to remove most of these artifacts occurs only after just 1 pixel of motion. To compare the performance of a SPAD array to conventional photography, they use an open source path tracer to synthesize photorealistic scenes. While both the conventional camera and the SPAD array were able to reconstruct scenes with motion, the SPAD array always had a higher peak signal to noise ratio. We can see that the SPAD array is able to capture more detail in both the dark and light zones of this dark nighttime scene. They also created a hardware prototype of the CFA on a SPAD array with a resolution of 496 by 254 to test the performance in real-life conditions. The prototype and algorithm worked well to reconstruct images in a variety of different scenes. In both dark and high dynamic scenes, the proposed algorithm is able to reconstruct good images compared to the naive solutions. And in this scene with a rotating color wheel, the proposed algorithm creates an image with clearly separated colors. In conclusion, this paper presents an algorithm to reconstruct colored images from a SPAD array, the best color filter arrays to use, and test these solutions on a real-life prototype.